Welcome to this deep dive into physics, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are diving deep into motion in a magnetic field. It's a central, and I must say, a highly scoring topic from our unit, moving charges and magnetism. And our mission, as always, is to make this concept so crystal clear that you walk into your exam hall completely confident. Okay, so let's unpack this a bit. You know that if a charged particle, say an electron, is moving, it creates its own magnetic field. That's clear. But what happens if we take this particle and shoot it into an existing magnetic field? What will the resulting force do? I mean, will it speed the particle up? Will it slow it down? Or will it just push it sideways?
That is a confusing thought. My first instinct, is that a force causes acceleration. So I would assume the particle accelerates, maybe gains speed along the field lines.
Yeah.
Something like that.
Right, and that's a very logical assumption based on everyday physics. But here's where it gets really interesting. Think about something high-tech, like a fusion reactor. If a strong enough magnetic field is applied, that field can hold super hot plasma. We're talking ionized gas at millions of degrees. It holds it in place, preventing it from touching the walls of the reactor.
Wow, so it's a kind of invisible bottle. Confinement.
Exactly, an invisible field holding something without any physical container. But here is the real puzzle. How can an invisible field hold something without slowing it down or speeding it up? That's the magic. And the answer is the core idea for today. The magnetic force is a sideways push.
A sideways push. Okay, that phrase itself, it sounds completely different from gravity or the electric force we've studied.
It is fundamentally different for two reasons. One, it acts only on moving charges. A stationary charge feels nothing. And two, the direction of this force is always perpendicular to the direction of the particle's motion. Always.
Wait, perpendicular?
Yes. And because it's perpendicular to the displacement, the force does absolutely zero work.
How can it do zero work? If a force is acting and the particle is moving, there is displacement? No. So work should be done.
But that's the crucial point. Work is the dot product of force and displacement. It's only the component of force along the direction of motion that does work. Since this force is always at 90 degrees to the velocity, it's never helping the particle speed up or slowing it down. It only deflects it.
I see. So the force is changing the direction of the velocity vector, which is an acceleration, but it's not changing the magnitude of the velocity. The speed is constant. That geometry is still a bit difficult to visualize, I must say.
Okay, let's lock in a strong mental image, an analogy. Think of a ball tied to a string, and you're swinging it over your head in a perfect circle.
Okay.
The tension in the string is constantly pulling the ball inwards, right? That's your centripetal force. And that pull, that tension, is always perpendicular to the ball's velocity at any given instant.
Right. It's always pointing to the center of the circle.
Exactly. So the ball goes around and around at a constant speed. The string is doing zero work on it, but it's forcing the ball to follow a curved path. A charged particle in a magnetic field behaves exactly like that ball. The magnetic force is the invisible string.
So the magnetic field is just providing the centripetal force.
Yeah.
It's the agent constraining the particle. That makes a lot of sense. It explains why the speed stays constant.
Precisely. So now picture a glowing blue particle entering a region where the magnetic field is, say, pointing straight out of the screen towards you. The moment it enters, the field exerts a perpendicular force, a sideways push. The particle turns. And as it turns, the force also turns, always staying perpendicular. The result is a perfect circle, or sometimes a spiral, and this predictable circular motion. It wasn't just a curiosity. It was a huge breakthrough for scientists in the early 20th century. It allowed them to control particles, which led directly to inventions like the cyclotron. The geometry is just so elegant. Now that we have this picture in our minds, let us see how NSERT formally defines this whole interaction. It combines both electric and magnetic forces into a single, beautiful expression, the Lorentz force.
Okay, where can I find the exact definition?
If you look at section 4.2.2, it defines the force when both fields are present. Could you please read that expression for us?
Yes, it says, the force on an electric charge Q due to both of them can be written as FFQE plus VXB. This is called the Lorentz force.
Excellent. The electric part, QE, is simple enough. It acts along the E field. But let's focus on that magnetic part, QVHEB, that V cross B, the vector cross product. That is the mathematical code for the perpendicular push.
The cross product is what guarantees the final force vector is perpendicular to both the velocity and the magnetic field, right?
Absolutely. That's its entire job in this equation. Now, this math leads us to 4 crucial steps or cases for understanding the motion. Let's go through them. Step 1. This is the simplest, cleanest case. The particle's velocity v is perfectly perpendicular to the magnetic field B. Here, the force is maximum, QVB, and it acts as the centripetal force, MVAHE. The result, uniform circular motion.
Okay, that's our ball and a string case. But what happens if the particle enters at, say, a 30-degree angle instead of 90?
Good question. That brings us to step 2. We have to resolve the velocity vector, v, into two components. One component parallel to the field, which we call v parallel, and one component perpendicular to the field, v perpendicular.
Okay, so we break it down.
Yes. And now the v parallel component remains completely unchanged. It's unaffected. Why? Because the cross product of two parallel vectors is 0. So v parallel cross b is 0. No force. That part of the motion is just a straight line.
Ah, so only the perpendicular component, v perpendicular, actually feels the force and causes the curving?
Exactly. Which brings us to step 3, the calculation. We equate the magnetic force from the perpendicular component, which is q times v perpendicular times b, to the centripetal force, m times v perpendicular squared over r. You solve that equation, qv sub b OP equals mvr. You get the expression for the radius of that circle. The radius r equals mvr divided by qb. And finally, step 4 is putting it all together. You have circular motion from v perpendicular, and at the same time, you have straight line motion from v parallel. What path do you get when you combine a circle with forward motion?
A spring shape, a helix, a spiral.
A perfect helical path. A corkscrew motion. That's the general case. The circle is just a special case where the forward motion is 0. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROSAM.com. Now let's use that radius formula for a quick example. Let's say an electron is moving perpendicular to a 0.1 Tesla field. That's not a very strong field. And it's moving fast, maybe 2 by 106 meters per second. If you plug those numbers into r equals mv/b, the radius comes out to a tiny 0.114 millimeters.
Wow, that's small. The path is curved very sharply then.
Very sharply. It shows how effective magnetic fields are at controlling even fast particles. And this leads us to the most fascinating and I would say exam favorite detail. The time period of this rotation. The time for one full circle, the period t, is the circumference, 2r, divided by the speed, v perpendicular. Now watch what happens when we substitute our formula for r into this equation. T over VOO times MVO QB. You see what happens?
V perpendicular, it cancels out.
It cancels out. The resulting formula is T equals 2 VO QB.
Wait, so the time it takes to complete one circle is completely independent of the particle's speed and its radius. That seems very counterintuitive. How can a faster particle take the same time as a slower one?
It's an incredibly elegant piece of physics. Think about it. A faster particle has more inertia, so it tries to go straighter. It needs a bigger force to turn it. But the magnetic force, FQVB, is directly proportional to the speed v. So a particle going twice as fast experiences twice the force.
So the force automatically scales up at the speed.
Precisely. And that doubled force pushes it into a circle with exactly double the radius, so it has to travel double the distance at double the speed. Takes exactly the same amount of time.
The bigger path is perfectly compensated for by the higher speed. That makes it click.
This constancy is the key principle behind the cyclotron. Because the period is constant, they can apply an electric pulse at a fixed frequency to speed the particle up again and again. Okay, now let's be very careful. We need to tackle 3 silent killers. These are common misconceptions that can cause you to lose marks in conceptual questions. First one, the wrong idea. Magnetic force speeds up or slows down charges. It seems logical. Force means acceleration. But is it right?
No, because we just established the work done is 0 because the force is always perpendicular, so kinetic energy can't change.
Exactly. So the correct idea is that the magnetic force only deflects. It only changes direction. Our remember hook is speed is constant. Only direction changes. Second silent killer, the wrong idea. A stronger magnetic field always exerts a stronger force. Can you give me a situation where you have an enormous magnetic field, but the force on a moving charge is 0?
Yes. The angle. If the particle moves parallel to the field lines, sin 0 is 0. The cross product is 0, so the force is 0.
Perfect. So the correct idea is that force depends on the angle, F QVB sin. The remember hook is perpendicular gives max force, parallel gives 0 force. Now the third one, this one's a bit tricky. The wrong idea. All particles in a field have the same period regardless of speed or mass.
We did say the period is independent of speed and radius, so that part is true, but the formula was T, M, QB, so it does depend on the mass M and the charge Q.
It is highly dependent on them. The correct idea is that the period is independent of speed, but it depends directly on the mass to charge ratio. So our remember hook is Faster particles take a bigger path but finish in the same time. But a heavier particle, like a proton versus an electron, will take a longer time. Okay, to lock all this in for the exam, let's create some memory anchors. First, a phrase. Just keep this in your mind. Magnetic force is a perpetual perpendicular push. It curves the path without changing speed. That one line covers the geometry and the energy aspect. Next, a physical gesture. Use your right hand. Curl your fingers as if they are tracing a circular path. That's the particle's motion. Now point your thumb straight up, perpendicular to the circle your fingers are making. That thumb is the direction of the magnetic field B. This gesture physically locks in that perpendicular relationship. And finally, an association. Imagine a skier spiraling down a mountain. The direction of the slope straight down is like the magnetic field line. The skier is the particle spiraling around it. The steeper the slope, the stronger the field, the tighter the spirals. Okay, let's wrap up with a quick 3-point summary of the key exam facts. Summary point 1. The magnetic force is given by FAAQ VXB. Because it's a cross product, the force is always perpendicular to both velocity and the field, and therefore it does zero work. Summary point 2. In a uniform magnetic field, a charged particle will follow a circular or a helical path. Crucially, its speed will remain absolutely constant. And summary point 3. The radius of the path, r, is mvqb. It depends on momentum. But the period of rotation, t, is 2 mqb. It is independent of speed and radius. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you for joining us for this deep dive. We hope you study well and score maximum marks.